Hi everyone. So sorry for the delay because of technical difficulties. So today it's my pleasure to introduce Olivia, who's going to talk about deductive systems and Grothendieck topologies.
Thank you, Theo, for the invitation. So I will talk about the proof of theoretic relevance of the notion of Grothendieck topology in this talk by showing that there is actually a proof theoretic equivalence between the ordinary proof system for geometric logic over a given geometric theory and new proof systems based on this fundamental notion of Grothendieck topology. The interest of these equivalences lies on the fact that these new systems that we will introduce will have only two inference rules, while the traditional systems, as you know, have between 15, 17 rules, which of course makes the proof theory quite complicated in general. So we will indeed argue that in many situations these new proof systems that are based on Grothendieck topologies allow for more efficient calculations in connection with constructions that have a natural logical interest. So where do these equivalences come from? Well, they come from topos theoretic bridges. So for those of you who have attended my course at the Laboratoire Mix, you know that topos theoretic bridges arise when you consider topos theoretic invariants in connection with different presentations of a given topos. So what I'm going to present today is a very specific application of that technique in connection with the invariant notion of subtopos. So what we will do specifically is to calculate subtoposes of the classifying topos of a theory. And this computation of this invariant in terms of the syntactic side of the theory, which is used to build the classifying topos of the theory, will yield a bijective correspondence with the so-called quotients of the theory. A quotient, by definition, is a geometric theory written over the same signature of the theory, which extends that theory. So that whatever is provable in that theory is also provable in the quotient. It turns out that the subtoposes of the classifying topos of a theory are in natural bijective correspondence with the quotients of the theory, and therefore the quotients of the theory can be investigated by means of topos theoretic means. This becomes interesting because when you go to the topos level, you can profit from the existence of alternative presentations for toposes that are not necessarily always of syntactic nature. They can be of whatever nature. In fact, as we saw in the course, a given Grothendieck topos is in general associated with infinitely many different presentations, possibly belonging to different areas of mathematics. So this characterization of quotients of a theory in terms of subtoposes paves the way for a multidisciplinary investigation of that theory by using tools possibly coming from any area of mathematics. So of course, in this presentation, we will focus on one very particular setting, which is when we present our classifying topos as the topos of sheets on a site of a certain kind. And then we will describe what happens. So how this correspondence between quotients and things expressed in the language of that site work. And this will give us these equivalences of proof systems. So I will first explain, I will review the basic background necessary for understanding these results, and then towards the end of the presentation, I will discuss a few applications so that you can appreciate the power, the computational power of these tools. Okay, so let's first recall the setting that we are going to investigate, so the setting of geometric theories. So what is a geometric theory? Well, here we talk about theories formulated in a first-order logic, in a constructive intuitionistic first-order logic. We focus on theories whose axioms can be presented in a particular form. Whose axioms are sequence of this kind. Phi entails psi in a certain context X. Now, and phi and psi are required to be formulas of a certain kind, namely the geometric formulas defined in the first point of the definition. So a geometric formula by definition is any formula that can be built starting from atomic formulas by only using finitary conjunctions, infinitary disjunctions, and existential quantifications. So this logic is called in the model theoretic literature positive existential logic. Now, it turns out that, of course, not all theories arising in mathematics have an axiomatization of this kind, but you can always operate on them in order to eventually arrive at such an axiomatization. For instance, if you start from a finitary first-order theory, there is a canonical procedure to make it geometric, which is called the Morligization. So this procedure consists essentially in making every first-order formula, finitary first-order formula, expressible in the language of the theory, equivalent over an extended signature to a finitary geometric formula. So what you do is to extend your signature in such a way that semantically at the level of the set-based models, you get an identification between the models of the original theory and those of the new theory, but syntactically you have a richer syntax so that you can express in geometric terms all the finitary first-order formulas expressible in the language of the original theory. I will not go into the details of this because we are not going to use this construction in the talk, but I wanted to mention it for clarifying the level of generality of geometric logic with respect to classical finitary first-order logic. Okay, so as we saw in the course, geometric logic is particularly important because of the connection with Grothendieck topos theory, because every theory that you can formulate in that way admits a classifying topos, which can be built in a canonical way by taking the category of shapes on the geometric syntactic side of the theory. And in a moment, we will review all of these notions.
So,
yes.
Non-geometric formulae are those with negations?
In particular, but you can also build formulas by using implication and also universal quantifications, and these are not allowed. But actually, you can always, through this process, replace any formula that you can write in finitary first-order logic with a geometric one, of course, in the extended signature.
Yes. Does this Moralization use classical logic, or is it compatible with purely intuitionistic theories?
Actually, it is based on classical logic in the sense that what you do is to introduce two predicates for each first-order formula, and one will be the complement semantically of the formula. So you will remain inside classical logic. So in fact, the equivalence Yes, I see that someone yes provides more details about this construction. Of course, we can talk about it at the end of the talk if you are interested. So actually, what you do is to make the theory geometric by adding artificially negations that don't exist in the geometric setting and all other things. And in fact, the semantic identification that you get between the models of the original theory and the models of its moralization works only for Boolean categories. So in general, the models will be different. So it is fine if you see you are interested in investigating first order theories in terms of their model theoretic properties, like in classical logic, because for instance, first order completeness corresponds to geometric completeness of the moralization. So you have a good transfer of properties, but from the classical setting to this geometric setting, which is inherently constructed intuitionistic. I'm not aware of whether people have introduced variants of this for intuitionistic first order logic. Okay, now let's recall this other construction that we had introduced in the course. The construction of the so-called syntactic category of a geometric theory. This is fundamental for building the classifying topos, as we said. Now, the idea is to have a first order generalization of the notion of Lindenbaum-Tarski algebra of a propositional theory. So when you build the Lindenbaum-Tarski algebra, you take the provable equivalence classes of propositional formulas written in the language of your theory. And you have an order between them, which corresponds to provable implication. And here what's going on is simply a generalization to the setting of first order logic of that construction. So instead of having a lattice, you have a category, which is a richer structure. So the objects of this category are the geometric formulas written in the language of the theory, considered in a given context and up to renaming equivalence. Of course, you want to allow yourself, for technical reason, the possibility of renaming contexts. Okay, so we take these as objects. And notice that in the definition of objects, there is no proof of theory involved. But in the definition of arrows, yes, because you define arrows in the syntactic category as the provable equivalence classes of geometric formulas that are provably functional from the domain formula to the codomain formula. So as you can see, this free sequence here express the functionality axiom. So here it says that if you have something in the domain, there should be something in the codomain that corresponds to it under theta. Here it says that theta is a well-defined graph of a function from the interpretation of phi to the interpretation of psi. And here it's the functionality axiom that a given element in the domain cannot be associated with distinct elements in the codomain. Okay, so this is how the category is defined in terms of objects and arrows, and we have a notion of composition for these arrows, which is like the relational composition, because here, of course, arrows are identified with their graphs. So this is, of course, the natural way to define the composition, and of course, we have identities. You see here, we are using renaming, so that we can write a provably functional formula which plays the role of the identity. So as you can see, it is a very tautological construction, as you are used to in the propositional setting. So there is a question. but it has disappeared. So
Yes.
maybe after the end of the talk, okay. Okay, now let's review the notion of Grothendieck topology, because what we are going to do in order to obtain this new proof system is to consider Grothendieck topologies on those syntactic categories. So a Grothendieck topology on a category is a way of assigning to each object of the category a collection of so-called sieves on that object. So recall that a sieve on an object C of a category is simply a collection of arrows going towards that object, which is closed under composition on the right. So the basic condition is that if F lies in S, then F composed with any G that has codomain the same object as the domain of F also should, its composite also should belong to S. Okay, so we clarified in the course the technical necessity of closing under composition on the right. Of course, sieves can always be generated from arbitrary families of arrows with a fixed codomain, because what you do is to take the collection of all the arrows that factor through one of the arrows in the family. And in this way, you get the sieve generated by that family. In fact, sometimes it's natural to specify the covering sieves for a Grothendieck topology by means of some closed formula that they should satisfy. Some other times, Grothendieck topologies can be naturally specified by in the language of pre-sieves. So you just specify some families, not necessarily sieves, that you want to be covering, in the sense that the sieves generated by them are covering. It really depends on the situations you are in. So typically in geometric situations, Grothendieck topologies are presented in terms of generators. And therefore, and these generators arise from pre-sieves. So the sieve condition comes later for these technical reasons. Okay, now, so Grothendieck topology consists in giving for each object of the category a collection of sieves on that object, in such a way that some natural conditions are satisfied. So the first condition is a trivial one, so the condition that every maximal sieve on any object of the category should be in the topology, should be covering. So the idea of this covering sieves is that they should express intuitively the idea that the object C is covered by the domains of the arrows belonging to the sieve. So it generalizes what goes on in topology when you cover an open subset U of a topological space by some open subsets U. In fact, the logic we are going to treat, geometric logic, has this name because it has a direct topological geometric interpretation. We will see that in our correspondence, the logical disjunctions will correspond to covering sieves, namely kind of categorical unions. Okay, so the first axiom doesn't need any explanation, because of course, if we take like the identity on any object, well, the identity arrow, of course, they should cover that object. The other two are the crucial ones. So second axiom is the so-called stability axiom. It says that if you have a covering sieve on an object C. And you have an arrow towards that object. So here you can consider the pullback sieve. So by definition, it consists of all the G such that F composed with G belongs to S. So the condition is that if S is covering, then also F upper star of S should be covering. It's a very natural condition. If you think about what happens in the topological setting, of course, you see if you have an open set U, which is covered by some UI, of course, when you pull back here, what you get is UI intersected with B and J intersected with B. And of course, you see, if here it covered, it continues to cover when you intersect with B. Okay. So this is the stability axiom. And then we have the third axiom, which is the so-called transitivity axiom. So the transitivity axiom can be interpreted as a kind of converse to the stability axiom in the following sense, that if you have a covering sieve S on C, and you have another sieve R on the same object, well, actually, the idea is that you can use S to test whether R is covering. So to do this, you consider all the pullbacks of R along the arrows belonging to S. And the condition is that if all of these sieves are covering, then R itself should be covering. So you see, you deduce the property of being covering from the fact that all the pullbacks of a certain kind are covering. So it is in this sense that it represents a kind of converse to that. Okay, that's it. So as you can see, it's very simple. It's a very, very elegant natural notion. You have nothing that you would consider unnatural or unnecessary in order to define a general notion of covering the family in a categorical setting. Okay, so by definition, a site is a pair consisting of a category and a Grothendieck topology on it. And Grothendieck toposes are typically built by considering the categories of sheaves on sites, as we explained in detail in the course. Okay, just a few examples of Grothendieck topologies, which we had already reviewed in the course. So of course, in connection with any small category, there is always the trivial topology that we can consider, because if we take as covering sieves just the maximal ones, of course, all the axioms of Grothendieck topologies are naturally satisfied. This is typically what you do when you have no when you are in a combinatorial situation in which you don't want to you have no non-trivial covering relations you want to take into account. Okay, of course there are many different examples of Grothendieck topologies that you can consider even on a fixed category. You see, in general, if you fix a category, there are infinitely many Grothendieck topologies that you can put on that category. So the notion is really extremely general and flexible. Here are just some a couple of examples to fix the ideas. One important class of topologies that can be defined on any categories is the so-called dense topologies. So you say that the covering sieves are the stably non-empty ones. So the sieves S such that this condition here holds. Okay, then of course we have already argued that the classical covering families in topology give rise to Grothendieck topologies on the categories of open sets of topological spaces. So these are the open sets are considered as poset categories, whose objects are the open sets and whose arrows are the inclusions between them. Okay, and more generally, this is interesting because you see here in defining this, we haven't referred to the points of the space. We have just referred to the lattice theoretic structure of on the open sets of the space. So you see this definition makes sense more generally for a frame. So if you have a complete lattice such that arbitrary joins distribute with respect to finite means, in other words, a complete Heytig algebra, also called a frame, then you can define a Grothendieck topology on it by taking as covering families those families that cover in the frame theoretic sense. Okay. Now, let's talk about our main object of study for this presentation, which is the syntactic side of the theory, of a geometric theory. So we have already defined the geometric syntactic category of geometric theory. What is interesting is that we can define in a very natural way a Grothendieck topology on it, called the syntactic topology, by considering as generating covering families, those families in the syntactic category which cover in a logical sense. You see, so you take, you stipulate that a small family of arrows in the syntactic category covers with respect to this topology, if and only if the sequent, the corresponding sequent which asserts that this formula here appearing in the codomain is covered by the formulas appearing in the domains, you see, through the provably functional formulas that go from the domain to the codomain. So this sequence is provable in the field. So here, as you can see, you have a direct connection between provability in the sense of logic and being covering in the topological geometric sense. So I anticipated the idea, which was that covering in the logical sense means you have a disjunction that is equivalent to the given formula. And of course, covering in the topological sense, we are very used to this notion from topology or topos theory more generally. Okay, so this is the fundamental connection. So what is interesting about this construction is that basically the proof theory of your theory T is captured by this site. And this site has actually two components, because we have the syntactic category, which already embodies a lot of the proof theory of the theory. And then you have the Grothendieck topology, which adds further information. So in some sense, the information is split across these two components. It's not concentrated in a single entity. It's like articulated between these two components. And this is why we are able to replace the classical proof system of geometric logic, which has 17 inference rules with a much simpler proof system over the syntactic category, whose inference rules are just 2, because they correspond to the axioms, the non-trivial axioms for Grothendieck topologies. You can do this, which looks like a miracle, because you encapsulate a part of the complexity of the proof theory already in the syntactic category. And therefore, what remains can be simplified. See? Because already the syntactic category is a complex proof theoretic object, because if you think about how the arrows were defined, they are already provable equivalence classes of formulas. So you see, in fact, it's called the syntactic category, but maybe one could have called it more correctly proof theoretic category, because it's already a proof theoretic object, you see. If you had not had the provability at that level, you would have needed to encapsulate more at the level of the Grothendieck topology. You would have had to take a richer Grothendieck topology. But this way of articulating things, as we will see, will allow us to have proof systems that are as simple as possible. Of course, this is by no means the only possibility, because this, from our point of view, represents one site that defines the classifying topos. But of course, one can take any other site of definition for any other possible choice of site of definition for the classifying topos. You will have another proof system associated with that site that will be equivalent to the classical one. So in fact, in this talk, I'm going to focus on 2 special cases of different nature. This one, and another kind of site that is the trivial site, which we can use for representing theories classified by pre-shift toposes. So I will, in the talk, I will just focus on these 2 particular cases, but the general method applies to any possible site that you can, or in fact, more generally, because it is based on a topos theoretic invariant, which is the notion of subtopos. In fact, it can also be extended to any other presentation of the classifying topos by means of other kind of objects, such as groupoids, quantals, whatever. So here, to fix the ideas, I will just focus on these 2 particular cases, but the setting is much broader. Okay, but let's go step by step. Okay, here I have just recalled what a Grothendieck topos is. Well, as we saw in the course, is by definition any category which can be represented as the category of sheaves on a site. In fact, sites are the most common type of presentation for Grothendieck toposes. So in fact, originally Grothendieck defined the toposes like this. Of course, later on, people have also built different tools for constructing the toposes. But even today, sites remain the main tool for representing toposes, and for good reasons, because also from a computational viewpoint, as we shall see, they are particularly well-behaved objects. Okay, so a Grothendieck topos is any category that can be represented like that, and a morphism, a geometric morphism of toposes is a pair of adjoint functors whose left adjoint preserves finite limits. So in particular, when you consider the inclusion of sheaves on a site into pre-sheaves, you get a geometric morphism between those toposes, whose inverse image is the associated sheaf functor and whose direct image is the inclusion, because you have an adjunction between them, and it can be shown that the associated sheaf functor, namely the left adjoint, preserves finite limits. Okay. The main result on which we will build is the existence of classifying toposes for geometric theories in the sense of this definition. So a classifying topos of a theory is a Grothendieck topos such that for any Grothendieck topos E, we have an equivalence of categories between the category of geometric morphisms from E to that topos and the category of models inside E. And moreover, this equivalence is natural in E, meaning that if I go from E to, say, E prime through a geometric morphism of toposes, I should get a commutative square up to isomorphism. Okay, fundamental theorem that was proved in the 70s by the Montreal School of Categorical Logic. It was published in the book by Mackay and Reyes, 1977, First Order Categorical Logic. Every geometric theory has a classifying topos, which can be built like that by taking the category of sheaves on the syntactic side of the theory. And conversely, actually, you can regard every Grothendieck topos as the classifying topos of some theory. Because, in fact, talking about the theories or talking about sites is essentially equivalent. You see, you can attach a site to a theory, for instance, the syntactic site. But conversely, you can also attach a theory to a site in a canonical way. So that the classifying topos of that theory can be identified with the category of sheaves on that site. So in fact, you can think about, I mean, you have two labels, toposes. So this is the label where invariants live. And then you have the concrete label of the presentations for toposes. And here you find the sites, theories, in the sense of axiomatic presentations, and many other objects that can be used for presenting toposes. So in particular, in this talk, we are going to establish connections, you see, like this, between sites and theories by using toposes as bridges between them. Okay, now a very important point for those of you who do proof theory, there is in topos theory a very important notion, Morita equivalence, between geometric theories, meaning two theories that have the same classifying topos. In fact, there are many examples in mathematics of theories even belonging to different areas, apparently completely unrelated, that are Morita equivalent. This is a very general, broad notion of equivalence of theories that relates to bi-interpretability, which is the more traditional notion of equivalence between theories, in a very interesting way. In fact, when you have bi-interpretability between theories, you also have Morita equivalence. In fact, you can interpret categorically bi-interpretability between two theories, T and T prime, by saying that you have an equivalence between their syntactic categories of, or some small completions of these syntactic categories. You see, because when you have a bi-interpretation, it means essentially that you can associate with any formula in the language of the first theory, a formula in the language of the second, and conversely, so that you obtain like a complete dictionary. So in a sense, when you talk about the bi-interpretations, you have in mind some kind of a syntactic dictionary that directly relates to the theories. So of course, this in practice can be something very useful, but in fact, when you analyze the theories from a topos theoretic point of view, you discover that most of the equivalences of theories that arise everywhere, both in computer science and in mathematics, do not come from this kind of dictionaries. So you need to take this more general notion to connect the theories with each other. The good news is that, of course, this notion of Morita equivalence is more complex, but you can profit from topos theoretic tools to make a connection between two Morita equivalent theories, precisely by using the common classifying topos as a bridge. So typically the transfer processes that you can still make between theories will not be induced by dictionaries. They will be induced by invariants that live at the topos level. So what you will do is to compute how invariants living at this level express in terms of the one theory. So suppose you will get a property PT, and on the other hand, you will obtain a property Qt prime. And it is in this way that you will establish connections. You see, you go through a third object in which the integration between T and T prime takes place. So you see, in general, you will not be able to relate in a linear way. You will have to, in a sense, embed the two theories in a third space that contains all of them, and use this third space to make the transfer. Yes.
Is this decidable?
What is decidable?
Is this equivalence?
No, I mean, in general, of course, these are very high-level tools, so you don't really control them algorithmically necessarily. It depends. So, of course, it depends on the situations. No, you don't have any general decidability result, but you can still, for practical purposes.
You just have techniques.
You have techniques. Yes, of course. There are a lot of techniques, algorithm, and but you don't have a completely general method. Here, essentially, you are at the very core of mathematics as a whole. So you cannot expect, you see, to have things that apply uniformly. But of course, in particular settings, you can try to find algorithms. And in general, topos theory is computationally very, very effective. And I hope already to convince you of this by illustrating the examples towards the end of the talk. Because we will be able to compute things that, at least to me, don't seem easily accessible by using traditional logical techniques, precisely by computing, classifying toposes, sites, etc. Okay. So I wanted to make this point because it is not necessarily relevant for the technical contents of this presentation, but it is very important to understand the spirit in which we work. In fact, the second example we are going to discuss already illustrates the lack of a general bi-interpretability lying at a certain level, but the presence of a partial bi-interpretability that can be used to make the transfer induced by a bridge. Because you see, sometimes you might miss by interpretability at a certain level, but you could still have it by restricting to some special class, etc. So in a sense, it's not that bridges totally replace dictionaries. They provide, in my view, the most natural conceptual architecture for making translations. But of course, in terms of practical implementations, it's always useful to look for partial dictionaries whenever they can exist. But being aware of the fact that in general, they won't be there. So you will have to have this more general view. Okay. So now the bridges that will induce our proof of theoretic equivalences, as I already anticipated, are induced by a particular invariant, the notion of a subtopos. So a subtopos, by definition, is a geometric morphism whose direct image is a full and faithful functor. So this is called an inclusion. So we say that a geometric morphism is an inclusion if the direct image functor is full and faithful. Of course, we have already encountered important examples of inclusions, which are the inclusions of a topos of sheaves into a topos of pre-sheaves. These are, in a sense, the canonical examples of inclusions. In fact, one can show that if you have a topos presented as the category of sheaves on a site CJ, the geometric inclusions towards this topos. So for technical reasons, you consider geometric inclusions up to equivalence, you see, in the sense that you want to consider two inclusions to be equivalent when you have an isomorphism that makes the triangle commute. So that you can really identify, you see, with the full subcategory. So if you have a topos represented like this, you can classify all the inclusions, all the subtoposes of this topos in cytotheoretic terms. So the subtoposes of the topos of sheaves on a site correspond precisely to the Grothendieck topologies on the category C, which contain J. So essentially, it means that you can consider any inclusion into E as an inclusion of this canonical type, induced by a Grothendieck topology J, which contains, J prime, which contains J. Of course, if you have a Grothendieck topology that is richer than a given one, of course, when you take the category of sheaves, here you get a subtopos of the other category of sheaves. And of course, the left adjoint will be sheafification restricted to J sheaves. Okay, so already from this, you can see that this is an invariant that can be very easily calculated. Because you see, here we have the notion of subtopos, which lies at the topos level. And here we have at the site theoretic level a very natural notion, the notion of Grothendieck topology, that refines an existing topology. So it is a very natural site theoretic notion. Typically, topos theoretic invariants are more difficult to calculate. If you take like the random invariant, it's not even guaranteed that you will find like explicit recipes for calculating it. Think, for instance, about cohomology. Typically, even in particular cases, it's something very hard to compute. But on the other hand, there are many topos theoretic invariants that can be computed even in an automatic way. And this is an example. You see this notion of subtopos. It is a non-trivial invariant, but it can be calculated explicitly. Of course, this result is by no means trivial. So it takes some work. But still, it is what you naturally expect. You see, it's not something like a counterintuitive or. Okay, now we look at this invariant from the logical viewpoint. Because here we have given a cytotheoretic description of this invariant. Now we look for a logical description. And also on that side, we get something very natural. Because if we have a geometric theory T, and we consider its classifying topos, the subtoposes of this topos correspond bijectively to the so-called quotients of the theory. This is a theorem that I proved already in my PhD thesis, and it is published also in my book, Theories of Site Toposes. And in fact, the proof is not particularly difficult. In fact, it exploits the previous correspondence applied to the syntactic side of the theory. And this is very useful because you see that the notion of quotient is a natural notion from the logical viewpoint. A quotient is simply a geometric theory that extends the given theory over its signature. So you don't change the signature, you only add more sequence, more geometric sequence over it. So as you can imagine, this is very relevant in connection with probability assertions, because when you look for when you want to investigate when something is provable, first you fix the language, and then you fix like your deductive system, the language, and then you try to characterize what you can prove inside that system. So essentially you investigate the quotients, you see, of the basic theory, if you want, the empty theory that you write over that language. Okay, so we have this bijective correspondence. Of course, you have to consider quotients up to provable, to like syntactic equivalence. So you consider two quotients to be equivalent in this sense if they prove exactly the same geometric sequence over their signature. Okay, and like this, you have this correspondence. Okay, so already from this, you can start deriving logical results from topos theoretic tools. For instance, it is known that when you consider the collection of subtoposes of a certain topos, this has the structure of a co-heighting algebra. So it means that if you reverse the order, which is what happens when you go to quotients and you introduce the order between quotients, which is the intuitive one, saying that t prime is less than or equal to t second if and only if everything that is provable in t prime is provable in t second. When you introduce this, it means that by means of this bijective correspondence, you get a heighting algebra structure on the collection of all quotients of a given theory, considered up to syntactic equivalence. So you see here I have a picture in which I have like represented lattice structure at the topos theoretic level, which gives rise to lattice structures that are perfectly isomorphic to that structure at the level of all the theories classified by that topos. So of course, these theories could in principle belong to different areas of mathematics, but they will all be associated with the same topos, and therefore whatever happens at this level will automatically have ramifications in all these contexts. Okay, so this also is a result that within the realm of geometric logic was not known, and which is, from my point of view, quite hard to prove by using the classical logical techniques. In fact, at the end of this presentation, I will give you an explicit axiomatization for the heighting implication between two theories, which I was able to derive from the corresponding description of the heighting implication between Grothendieck topologies. And you will see that it is by no means a trivial construction. It would have been very difficult to imagine that by using the traditional techniques. While by using these bridges, you can compute in the realm of Grothendieck topologies and then transfer back. Okay, but I just wanted to anticipate this as a kind of motivation, but many more interesting things will happen. Okay, just to fix the setting, this is what we shall exploit. You see, so we will have the classifying topos of our theory T presented as the topos of sheaves on some site Cj, and then we will look at the subtoposes of this topos from, on the one hand, the point of view of the site Cj, and on the other hand, the point of view of the theory T. So you see the same invariant will correspond on the left to the Grothendieck topologies on C which contain J, and on the other side, it will correspond to the quotients of T. So we will get a bijection. an order-preserving bijection between the quotients of T and the Grothendieck topologies which contain J. When I say order-preserving, here I have already given you the notion of ordering at the level of quotients. Here, the notion of ordering between Grothendieck topologies is the set theoretic one. So, topology contains another one if all the covering sieves in that one are also covering for that topology. Okay. So you see, here you are in the realm of logic. Here you are in the realm of topology, but you have a bijective correspondence. Okay, now in order to extract some computational results, we will focus on two particular cases. So the first case we will treat is that of the syntactic side of T, which we have already introduced. And the second case will be the situation in which our basic theory is of preshift type. We say that a theory is of preshift type if it is classified by a preshift topos. Now, it can be shown that if a theory is finitary algebraic, it is always of preshift type. So if, for instance, we work over the theory of rings, over the theory of groups, any theory whose axioms are just equalities between terms, so any theory that belongs to the realm of universal algebra, is of preshift type. Of course, this class is much broader. It contains also many theories that have a quite a different syntax. So you can have theories classified by preshift toposes whose syntax involves even infinitary disjunctions. So it is by no means limited to those theories arising in universal algebra. It is much broader. But still, you see, if, for instance, if you fix a language and you don't put any axioms at all, so you get the so-called empty theory, you can apply, you are in the setting of a theory of preshift type, because you have no axioms except from those of the meta system. And then you will be able to apply the techniques that we shall describe for this second setting. So if a theory T is of preshift type, its classifying topos can be represented like this, by taking the covariant set-valued functors from the category of finitely presentable models of the theory. And therefore, because the classifying topos has this form, we will get a bijective correspondence between the quotients of T and the Grothendieck topologies on the opposite of this category. In the first case, instead, we will get a bijective correspondence between the quotients of T and the Grothendieck topologies on the syntactic category, which contain the syntactic topology. Still, in both cases, because they both arise from the same kind of topos-theoretic bridge, we get a proof-theoretic equivalence between the classical proof system of geometric logic over T. So here I haven't given a formal presentation of this deductive system, but if you know the classical deductive system for first-order logic, it is just an adaptation of that for geometric logic. So you have like the basic axioms for equality substitutions, the basic inference rules, cut rule, Frobenius, etc. The rules for conjunction, disjunction, that for existential quantification. I have counted 17 between axioms and inference rules. Of course, you can find this in the references for more details. So you see, this is what we are referring to when we talk about the classical proof system for geometric logic. Over T, it means that we work over T, so we suppose that we also have all the axioms of T as additional axioms. If you don't want this, you have to you can take T to be empty theory, and so you just have the basic uniform axioms. Okay, so on the other hand, we have new proof systems based on the notion of Grothendieck topology. So you see, in the traditional proof systems, you deal with a sequence. So you have conditions for a sequence to be provable. In these new proof systems, we will have conditions for sieves to be provable. Okay. And in fact, what will be interesting is that probability of sieves will precisely mean that the sieve belongs to the Grothendieck topology generated by the things from which you want to prove, you see? So probability corresponds to generation of Grothendieck topologies, which is a problem that, as we shall see, is much more tractable from a computational point of view. So let's give the formal definition of these proof systems. So given a collection A of sieves in a given category C, we can define an associated proof system by taking as axioms all those sieves, because you might want to start from some sieves. Of course, you can always take the empty family if you like, but this is more general, and we will need this generality. So we take as axioms all those sieves plus the maximal ones, as it is natural. And at the level of inference rules, we will take precisely the proof-theoretic versions of the axioms for Grothendieck topologies. So we have a stability rule that allows us to infer such a sieve from that sieve, and the transitivity rule that allows us to infer R from Z and all these pullbacks. You recognize, you see, if the stability axiom for Grothendieck topologies said that if a sieve is covering, then all its pullbacks should be covering. The condition of provability corresponds to being covering in the topological sense. So you see here, it's natural to interpret it as an inference rule because you see, starting from the condition that R is covering, you deduce that F upper star of R is covering for any F. And here, as I told you, it's a kind of converse to that. You see, supposing that all these pullbacks are covering along the arrows of a covering sieve Z, then R is covering. So you see, it's whenever you have a closure operation, essentially you are in a proof theoretic, in an abstract proof theoretic setting. And what are the closed theories of these proof systems? They are precisely the Grothendieck topologies on the category that contain the sieves that we have taken as axioms. And what is the closure of a theory that can be formulated in this system? Well, a theory will be just a collection of axioms, but axioms are replaced by sieves. So what is its closure? Well, it is the Grothendieck topology generated by that family of sieves. By definition, the Grothendieck topology generated is the smallest Grothendieck topology that contains that family of sieves. Then you might wonder, can you calculate it? And the answer is yes. You can calculate it through different means that are computationally very effective. There is one way of calculating Grothendieck topologies by using trees. This is also very natural from a proof theoretic perspective, and also I think from the point of view of the computer implementation. But you can also have a closed formula for which I will present to you, for the Grothendieck topology generated by a family of sieves. And so, of course, depending on the situation, you might find it useful to refer to one or another. But still, these are things that are very akin to computation, both in general and in specific cases. Okay, now we will, let's describe how this proof-theoretic equivalences work. So we want to understand how to turn the problem of provability of a certain geometric sequence into a problem of provability in these new systems based on Grothendieck topologies. It works in a very simple way. So if you have a geometric sequence like this, written over the signature of your theory, T, you consider the principal sieve. Principal sieve means a sieve generated by a single arrow. So the arrow you take to generate this sieve is this one. You take the conjunction of the two formulas here, you see, and here you take the domain formula. So this is just a sub-object in the syntactic category. You take the sieve generated by this sub-object. This is what you have to do in one direction. In the converse direction, if you start from a covering family like this, which is the sequence that you attach to that? It is the sequence that asserts essentially that this is covering in the logical sense. That if you have something here satisfying psi, then it must come from something satisfying phi I for some I through theta I. So as you can see, it's very concrete, it's very explicit. And the result is that you indeed get a proof-theoretic equivalence, because these correspondences are compatible with respect to the closure operations that formalize the proof theory in the two systems. Because of course, you can extend these correspondences to arbitrary collections of sequence on the one hand and on sieves on the other. And once you consider these extensions and you close, you see that it's compatible with the closure on the one hand and on the other. And it is, and of course they are bijective. You see, when you start from U, you apply F and then G, you get back to the closure of U. And similarly, if you start from B, you apply G and then F, you get back to the closure of U. So you have really a very precise proof-theoretic equivalence between these two systems. Let's describe what happens in the second case, so where we start from a theory T, which is of preshift type, and we represent its classifying topos in that form. It's very, very similar, but here there is a phenomenon that of a kind of partial by interpretability that is interesting to point out. In connection with theories of preshift types, there is this key notion of T irreducible formula. This is a proof-theoretic notion. It's not just a syntactic notion, it's proof-theoretic. So we say that a formula, a geometric formula written in the language of the theory is irreducible if, when you regard it as an object of the syntactic category of the theory, it doesn't admit any non-trivial covering sieves. So you see, in a sense, you recognize the topological inspiration for this notion. So in topology, or I mean, more generally in topos theory, you say that an object A is irreducible if whenever you can cover it by some other objects, I, like this, through arrows. So imagine that this family here, is epimorphic, then you say that it is irreducible if for any such family there is a splitting of the identity through one of these arrows. You see, it's irreducibility in the topological sense. So if you compute this, which is a topospherotic invariant, in terms of an object of the syntactic category embedded in the corresponding classifying topos, then actually this object is irreducible in that sense, if and only if its image is irreducible in the topospherotic sense. But irreducibility is actually a condition that can be formulated purely proof theoretically, because, for instance, it implies indecomposability that you see if you can cover your formula by some other formulas, you see, which provably entail it, then of course this covering should be trivial. You see, this is one consequence of the irreducibility axiom. So as you can see, it's a notion that can be, that is a very natural logical significance. Of course, I mean, here for simplicity, I have not reported the explicit logical characterization of that, but you can find it in my book. Anyway, what is important about those formulas is that those formulas are precisely those that present the finitely presentable models of the theory. So actually you have a kind really of dictionary where you have on the one hand this category, and on the other hand this category here, which is a full subcategory of the syntactic category on the irreducible formulas. So you have this, which, because it is a categorical equivalence, you can really think of it as a dictionary. This is very, very useful because it allows you to turn things on the from the logical side to the more algebraic or semantic side here. You see, you replace a formula with the model which this formula presents. This is a generalization of the notion of finitely presented model of an algebraic theory. For instance, if you have an algebraic theory, what is the model presented by this formula? Well, it is the free model on two generators. So it is a generalization of that. In general, if you have a geometric formula which presents a model, this model is characterized by this universal property that the model homomorphisms from this to any other set-based model are in bijective correspondence with the elements of the interpretation of the formula in that model. So as you can see, if you take the formula true, here you get n cross n. And so any pairs of elements of n determines a unique morphism, so you get F2. So as you can see, it's a broader notion that encompasses what happens in universal algebra. And what is great about this is that actually, if a theory is of pre-shift type, and actually not just if, but if and only if a theory is of pre-shift type, you can cover every geometric formula by irreducible formulas. you can really cover it in the syntactic category. And in fact, this idea will be crucial for establishing the second kind of proof-theoretic equivalences. Because if we want to get a correspondence between the geometric quotients of T and the Grothendieck topologies J on this category, you see, you will need to turn sequence of arbitrary kind, you see formulated here, in terms of things there. So you see, you have to go through this smaller fragment for which you have a by interpretation. So what you will do is to cover everything here from with the things coming from there. Then you will apply the correspondence at that level and you will reconstruct. This is like the general strategy that we will implement. Okay, so this is the theorem summarizing the discussion I have made. So if we have a theory of preshift type, every finitely presentable model for this theory is presented by an irreducible formula, in the sense of the previous definition, and conversely, every irreducible formula presents a model. In fact, that result, that by interpretation, comes from a bridge. You see, you have two different representations for the classifying topos. You have this, if you want, semantic representation, but you also have, of course, the syntactic representation, which is always available. And you look at this invariant from the 2 points of view. So if you look at it from this point of view, you get actually every object of this category. Because, in fact, the irreducible objects of a preshift topos correspond precisely to, if the category is Cauchy complete, it corresponds exactly to the objects of that category. You can show this. So this clarifies this arch of the bridge. And on the other side, as I have told you, the irreducible objects of the classifying topos actually, well, it can be shown that they all come from the syntactic category, and if they come from the syntactic category, it means that they should correspond to irreducible formulas inside it. So you see, this bridge gives you the connection, I mean, this categorical equivalence that will be crucial for describing the proof-theoretic equivalence. Okay, here we are. So don't get scared by this heavy notation. I will explain on the blackboard. As I anticipated, if you start from a geometric sequence and you want to compute the sieves that correspond to that, you need this sequence to be presented in a certain form, because if you are not able to formulate them in terms of the irreducible formulas, you don't quite know how to get to the context of sieves. So what you do is to first put your sequence in that form. You see, by using the fact that you can cover every geometric formula by irreducible formulas, you can actually reduce to the case where you can put yourself in the case where the axioms of your quotient can be presented in that form, where phi is an irreducible formula and all the other formulas arising here are irreducible. So you are able to suppose that you are in a situation like this. Because if you are not, you see, suppose that this is not irreducible. You can cover it, you see, by using a disjunction, and then you can, you see, a disjunction proves something if and only if all the things prove. And so this is how you can reduce to that case. Okay. Now, to be precise, here you suppose that you have, so one can show that you can rearrange, you can rewrite your axioms so that they take this form, where all these formulas here, these are T irreducible. And this is a geometric formula that is provably functional from this domain formula to this codomain formula. Okay, so supposing that we have arranged our axioms in that form, how can we build the corresponding Grothendieck topology? Well, we take each of this sequence and we associate a sieve to it. In which way? Well, we exploit this categorical equivalence. Okay, so we know that actually here we can take the models presented by these formulas, because they are irreducible and therefore they present some models. So first we consider this model here. In fact, the sieve that we are going to attach to this sequence will be a sieve on that object. So what we have to describe are the arrows that generate this sieve. There will be one such arrow for each element of I. And this arrow will be defined like this. So first we take the interpretation of this probably functional formula theta in the other model presented by that formula. So we take the interpretation of theta I in this. So this will go from, I mean, because this is probably functional at the semantic level, it means it is the graph homomorphism, which goes from the interpretation of the domain in the model to the interpretation of the codomain in the model. So we have this. Now, here, as you can see, we are taking the interpretation of the formula that presents that model. So inside here, I have the generators of this model. And I can take the image of these generators under this map. But now, here, I get an element of the interpretation of the formula phi in this model. Then, you see, by definition, by the universal property of that model, this corresponds precisely to a model homomorphism going from that model to that one. Remember the universal property I wrote earlier. And so in this way, I have got an arrow SI. an arrow in this category, FPT mod set op. And I take the sieve corresponding to that sequence as the sieve on this object generated by these arrows. That's it. This is how it works. So this is how the proof-theoretic equivalence works. So if we want to understand whether a sequence is provable in a quotient, what we have to do is to take the sieve corresponding to it, if it is already of the right form, otherwise you put it in that form, and in general, it will correspond not just one. If it is of the right form, it will correspond to a single sieve. Otherwise, it will correspond to several sieves. So you will have to check that all of those sieves are provable. But still, you have a direct connection between problems of provability in geometric logic and problems of belonging to a certain Grothendieck topology. And this can have a lot of applications. In fact, there is already a development of this in a particular setting that has been pursued by Coste, Lombardi, Roy in the setting of dynamical theories. So they take as basic theory a theory arising in in the context of universal Horn logic. So they take that as the starting point, and then they consider finitary extensions of them. And so they get a notion of dynamical theory that they studied by using trees. You see, they don't really use topos theoretic techniques, but the idea is similar. So there is a similar inspiration to these techniques. They have never really formulated things like at this level of generality, but what they have been developing is an approach to the proof theory of systems based on trees, and it is clear that these proof systems for Grothendieck topologies that we have introduced are in a sense behind this development. So I invite you also to look at their papers. Their presentation is much more concrete. But of course, here what we have been presenting is much more general, because in particular it allows us to work directly with the syntactic side of the theory, which is not what they do. And for some applications, as we shall see, it is very useful to directly work there, because after all, it is the universal model of the theory that you exploit in a purely syntactic terms.
May I ask
yes.
a stupid question? There is a French mathematician working on algebraic theories whose name is Marie-France Coste-Roy. Is there any relationship to this?
Yes, the same person. Yes, but these are, I think, all their works.
Why do you split the name? With Lombardi in between.
Because Lombardi also corresponds. Maybe it's just for alphabetical order.
Yeah, but
yeah.
That's her name is Coste-Roy. So.
But maybe when she wrote that, I'm not sure. Yeah, okay. Please.
There is also her husband with Coste.
Coste, yes.
There is Michel Coste and Marie-France Coste-Roy.
Okay.
So there is the two.
I didn't know that.
There is the two different on the
Okay, anyway, I think you will have no trouble in identifying this is what matters. Okay, so now I would like to convince you about the interest of these equivalences. The interest, as I already anticipated, lies in the fact that in many situations, checking that a sieve belongs to a certain Grothendieck topology generated by certain family of sieves is something much easier to investigate than probability within like a traditional logical setting. One reason for this is that you see that the proof systems that we have introduced have just two inference rules, because so when you have just two rules, you control things much better, as you can expect. And in fact, you can even write down formulas for describing the Grothendieck topology generated by an arbitrary family of sieves. Also, you can perform many other calculations much more naturally on the Grothendieck topology side than on the logical side. For instance, you can compute intersections of Grothendieck topologies very naturally in many settings. You can also obtain descriptions of the I-thing implication between Grothendieck topologies, and these are not things that are naturally tractable from a more traditional logical viewpoint. So to be more precise, here are some technical results that illustrate these points. So suppose that you want to calculate the meet of two Grothendieck topologies. This logically corresponds to taking the intersection of two theories. So what is the intersection of two theories in the same language? Well, it is the collection of all the sequences that are provable in one and in the other, when you consider them independently. As you can imagine, it is a hard problem if you start from two axiomatizations of the two theories to produce an axiomatization for the intersection. Let's look at the same problem from the point of view, from the geometric point of view of Grothendieck topologies. The problem becomes that of calculating the intersection of two Grothendieck topologies on the same category. So the intersection means that the covering sieves are precisely those that cover for each of them independent. Now, suppose that you have a basis for the two topologies. Basis means that you are able to present your topologies by means of kind of generators given by K1 and K2. So suppose that you have descriptions like this. So of the covering sieves as those that contain some family lying in the basis. So suppose you have things like this. S belongs to J1 if and only if it contains some T which is in K1. There are many situations in geometry where you can present your Grothendieck topologies in that form. For instance, the Zariski topology can be presented like this. You see, when you describe the covering sieves for the Zariski topology, you say these are the sieves that contain all finite families of localizations of a ring at elements that generate the total idea. Similarly, if you want to calculate the Grothendieck topology corresponding to the theory, say, of integral domains, regarded as a quotient of the theory of rings, you get a Grothendieck topology that is described in a similar way by using as basis the collection of morphisms of this kind, where the product of these elements is the 0. So I can tell you that in many situations of practical interest, Grothendieck topologies can be presented in terms of bases like this. But now, suppose that you are in those situations. For instance, when you deal with, say, the Zariski topos or integral domains, then you can very easily describe a collection of generators for the intersection of the two Grothendieck topologies. Because you can reason very simply like this. You can observe that because you have these two equivalences, you can put them together and write S belongs to the intersection if and only if S contains both a T belonging to K1 and a T prime belonging to K2. So you can write more compactly, S contains the union of something from K1 and something from K2. You see, this is a really topological idea. Very simple. But you see, when you translate this back into logic, it gives, for instance, an axiomatization, a concrete axiomatization for the intersection between the theory of local rings, which is classified by the Zariski topos, and the theory of integral domains. This is an example. I can tell you what it gives. Look, you see, we have solved our problem. As you can see, the axioms are perfectly concrete. They involve polynomials, you see, conditions, and you know that this is the intersection of your two theories. Personally, I would have not been able to find this in other means, you see. While topos theoretically, as you can see, it's very simple. You have a very simple idea. You see here, actually, you can see this disjunction. So this is the condition that comes from J1, and this is the condition that comes from J2, you see. But here it is perfectly formulated in logical terms. But it arises from that idea. Okay. Now, I told you that there is a closed formula for describing the Grothendieck topology generated by a family of sieves. So if you suppose your family to be stable under pullback, and in case it is not, you can, of course, always close it by taking all the pullbacks. You have a formula that gives you a characterization for the covering sieves for this Grothendieck topology. And it is a formula that is completely explicit, and you can use it for computations. I actually used it in my book for computing things and for proving in a completely mechanical way the deduction theorem for geometric logic through a calculation of a certain Grothendieck topology. So this is what I did. You see, this was a theorem that was not known before for geometric logic, and the proof I gave in my book is very simple, and it consists in calculating a certain Grothendieck topology. So, in fact, you see here, the idea is, you see, you start, so this sequence there corresponds to this subobject in the syntactic category. So what I showed is that if the principal sieve in the syntactic category generated by this subobject belongs to the Grothendieck topology generated over the syntactic category by the other principal sieve generated by the other subobject, you see the one corresponding to the premise of the sequence, then this relation between subobjects hold. This relation between subobjects means precisely the probability of that sequence. And of course, you can find the details in the book, but I can guarantee you that it is a perfectly mechanical proof. Even a computer appropriately, instructed, of course, you would have to give the computer a very rich meta system, allowing it to deal with sieves, geometric theories, etc. But provided you have that, this is a kind of calculation that even a computer, it's completely mechanical. There is no kind of real idea there. And also there is no case distinction. This also is important. You see, from a computational viewpoint, you don't have to say, okay, we have a huge disjunction or a huge tree. Because in fact, the formula I used is the closed one. You see this one. So by using this formula, you have no case distinction to make. Of course, in other situations, it might be more convenient to describe the Grothendieck topology generated in terms of trees. So you see, it really depends on the kind of applications we want. But still, as you can see, this is very, very computable, explicit. And yeah. So finally, as I had promised, here is the axiomatization for the Heyting implication between two theories. Again, it is by no means trivial. I will not even read it. So, no, it's pretty scary, actually, but it comes out of a computation, you see? And again, if you appropriately program a computer, you could have the computer find these results for you. Okay, so I think I'm done for today. Of course, I will be happy to take any questions you might have. Thank you.
Some questions. So there was one question that you said you kept.
Okay, yes.
From so I think it was from one of the earlier slides.
Okay, so
that means why not theta and phi entails psi, which.
Okay, so maybe I go on
the syntactic category.
syntactic.
So it's like the first slide.
This one.
Yes, yes.
Okay, so the question was.
Why is it not theta and phi entails like d dash psi?
Because you want theta to be the graph of a function going from the interpretation of phi into the interpretation of psi. So you see, imagine actually the language in which you work is the language of relations, and you want to put conditions on a relation for it to be the graph of a function. So the idea is you have two big sets X and Y and subsets A and B. And you have a relation at this level, so a relation like this. And you want to put the conditions for R to be G of F for some F going from A to B. So you see, the first condition you have to put is that if X, Y belongs to R, then X belongs to A and Y belongs to B. You see, so this is like the set theoretic version of the second axiom. So this is what is natural to do. Yes, please.
A very practical question.
Yes.
So, assume I have a development, say, in CAC.
Yes.
For natural numbers, I import it in Deductive. I have another one in HOL. I import it in Deductive.
Yes.
And I want to know if these two developments of natural numbers are equivalent. Would you do to answer that question? Yeah.
Well, you would have to introduce theories that formalize the different systems in which you work, because of course each system has its own vocabulary, has its own formal language.
Yes.
And so first you have to attach formal languages to the systems, and then you have to investigate which kind of equivalences you might have. Of course, it's important to have the broader point of view of Morita equivalences, because if you just look for dictionaries, you might not have them. You see, so you have to be open at the possibility of having Morita equivalences that don't boil down to by interpretations. But still, what I would suggest is to look simultaneously for the big picture, like trying to have certainly a Morita equivalence, because if you don't have a semantic equivalence, it means that they don't quite describe the same things. So you should try to get to a setting where you have a Morita equivalence. When you have a Morita equivalence, you can start investigating whether there are some partial forms of bi-interpretability that can be established for computational purposes, such as, you see what we saw for sieves and irreducible formulas. Typically, there are some forms of partial bi-interpretability that can be identified. Even when you are not able to identify any, you will still be able to perform translations by using invariants for inducing bridges. This is how I would approach the problem. So I think one limitation that we have at the moment concerning geometric logic is that it is a first order logic. So it doesn't treat higher order constructions, but in order to be able to have a treatment for higher order constructions, I am currently developing with my PhD students higher versions of the geometric logic based on working on relative toposes. So like the idea is that you should not only work over sets. You see, all the classifying toposes we have been considering in this talk are classifying toposes defined over sets. But of course, nobody prevents you from developing topos theory over an arbitrary base topos, which is not this one, which is richer than this one. So in this way, you can incorporate a part of the complexity of your theory in the base topos. And so in the end, you can increase the logical complexity, because you can have so this would be like the ground zero topos, but then you can have like chains of toposes defined over it, and you can jump one order higher every time you take a morphism. So for instance, by taking just one relative topos, one morphism, you are able to consider a first order theory as a propositional one, so a theory of degree 0. So you get from 1 to 0 by incorporating part of the complexity in the base topos. So in a similar way, you could treat like a theory, say, of order 2 as a theory of order 1 relative to a base topos that incorporates, and so on. So this is a subject of work in progress that we are doing. And following those developments, it will also be possible to cover not necessarily all higher order logic, but important parts, important fragments of higher order logic. So we will define a higher order geometric logic, which correspond to higher classifying toposes in the sense of relative toposes, or chains of relative toposes. And so thanks to that, I think we will be able to model in a very geometrically appealing way also higher order settings. Of course, the distinction between first order and higher order is also not so neat because it all depends on the choice of the language. You can try to reduce the complexity, you see, by enlarging the language. So another general suggestion that I can give is to not to be frightened at the idea of considering very, very large vocabularies. This is not really the tradition in logic. You see, traditionally people in model theory have been defining first order theories over languages with just one sort. You see, that has been the tradition. But in fact, when you develop this kind of techniques, you are naturally led to consider languages that can have infinitely many like sorts. And in fact, the bigger the vocabulary is, the greater are the chances of reducing the logical complexity of what you express. So you see, I think that for many practical purposes, maybe you could already do a lot by remaining in the realm of the first order logic, but with very large vocabularies. And so one could start looking at what is already possible to do through geometric logic over sets. And then with these further developments, it will become more and more powerful. But as you can see, it's already quite significant, the kind of improvement that these topos theoretic techniques can bring into like, more traditional logical tools. So I would be very keen to discuss about these things with your research team.
My colleagues.
Yeah.
Have any of these ideas or techniques been implemented in any like existing proof systems? Second, can you elaborate on the character of these Morita equivalences?
Sorry, the second question, the character.
Are they called Morita equivalences?
Morita.
Okay.
Yes, Morita. Yeah. Yes. So in terms of implementation, I mean, there are people. I mean, that are interested internationally in like implementations of geometric logic more generally into proof assistance. So it is a subject that is of a certain interest internationally. I don't quite know the current state of development in the different groups. So concerning us, it's something that we have recently started considering. So we are still at the very beginning of like choosing which systems can handle our needs more efficiently. Of course, you see, one problem with the implementation that we face is that there is a significant lack of macros for dealing with sites. And you see, in most, there is something. You see, in Lean, for instance, there are some category theory libraries, but not a lot, you see. So at the level of the meta system,
so at the moment, it's a problem of being able to nicely interact with sheaves and sites.
Also, yeah.
Yes.
Yes. So this is the first difficulty to overcome, you see, because we cannot directly implement unless the existing systems are enriched with more libraries to deal with sites, especially Grothendieck topologies and like categorically routine manipulations. So you see what I have been talking in the last months with several experts in proof assistance and different proof assistance. But in fact, we are not yet at the level, I mean, from what I could tell, where what the mathematician considers a routine categorical calculation is also routine for the machine. We are not yet.
Are you aware of what any of the bottlenecks specifically are for dealing with these things?
No, I think that the problem is that the libraries are not rich enough. So, I mean, they should be enriched with more things. And also, I mean, the rewriting systems, they also have to improve. So there are different sets of difficulties that need to be overcome before we can actually have a ground on which to implement. So from my point of view, based on the analysis of the last months, still we need some developments at the meta level. When these developments will have reached a relatively solid mature state, then it will be quite easy, I would say, to implement, because as you can see, it's very, very algorithmic, it's very computational, very explicit. So I just wait for further development of these libraries. We hope also to contribute through our research work to indicate ways to pursue this. So we are in contact with different research groups about this. And of course, any of you that is interested in collaborating is welcome to contact us.
Who's us?
Us? No, I mean the Grothendieck Institute, and yeah, because we are working on this, especially at the institute that we have funded 2 years ago. So also we have a postdoc opening on that at the moment, and yeah, so we are doing the selection at the moment. So we have already received several expressions of interest, but the evaluation, the formal evaluation will take place in a couple of weeks. So if you know of interested candidates, spread the word. Yeah.
So you mentioned the formalization of meta theory and over theory here, but perhaps if you look at the proof system for sieves,
yeah.
Perhaps you don't need to formalize many categorical things, no? Because
the problem is the rewriting of arguments, because you see, it's very easy when you compute with sieves to get huge formulas that if you don't have like the expertise of a classical mathematician to simplify, to put in a more, you can easily get unreadable statements. You see, an example is this formula here. This one. It's pretty unreadable, you see. So suppose that you give this formula to the computer and you ask the computer to use it in a blind way. It will end up, I think, very easily with even more unreadable formulas. So you see, the problem of rewriting is crucial. But rewriting also in a way that is as intelligible as possible to the human mind. So it's also a philosophical problem, you see, because you have to guide, in a sense, the computer to think like a human. Because it's not just getting the results, but also getting the results formulated in a way that makes sense to us. And of course, for us, you see, certain formulas written in a certain way with a certain shape are more naturally intelligible than others. But I'm not aware of many studies that have been done, like even psychological studies, I would say, you see, about how mathematicians tend to describe their knowledge, you see.
Two different mathematicians, two different descriptions. That's very easy.
Yes, but still there are traits in common. You see, it's not that mathematicians use...
if you practice proof assistance, you keep reading non-readable formulas, because proofs are non-readable formulas.
Yeah, but...
it's all the time, all the time. There is nothing you can do about it.
Yes, but there is worse you can get, because if you... you see, I really fear that, you see, if you feed the computer with that formula, and then you... Because you see, I was able to turn that form to apply it in an intelligent way, but I'm not sure that the computer would have been able, you see, because I told you, okay, it was mechanical, but it was mechanical modulo some familiarity with category theory, which is trivial for a human, but not necessarily for a computer.
These are tactics.
Kind of tactics. Yes, so you see, we recently organized a talk given by Yannis Lindberg, who is an expert on a lean tactic, which is called ASOP. So, and And we discussed about him, about what is available like inside the category theory, because there is a library of category theory like inside the Lean and an adaptation of that tactic to category theory. But I got the impression that what is routine for the mathematician is not yet routine for that system. Anyway, it's something we are considering. So we have launched this research project, and there are many actors involved. And of course, everyone is welcome to contribute. Of course, there is a lot to do, you see, so there is work for many, many people. And so we will understand more and more. And of course, it is also a subject that is developing quite fast. So we can hope that more tools will become available in a relatively short time. And then we will have the pleasure of seeing the computer like put topos theory in action. And but not only in that very specific setting I have been describing, but more generally, you see, the bridge technique is a very, very general technique that you can apply in connection with any sort of invariant. So ideally, one would need to feed the computer with a database of invariants and their characterizations on the one end, and equivalences of toposes, like Morita equivalences of theories on the other hand, and then the computer would combine them and generate new results. So I think that starting from this very specific case, which is relatively simple, but already non-trivial, would be a good idea, you see, in terms of research strategy. And then we could go on more generally for a computer implementation of the bridge technique more broadly.
I have another practical question. So if you use a proof assistant, you keep defining inductive types.
Yes.
And then the computer turns these inductive types into some computational means via eliminators.
Yeah.
But in all we do, in many cases, we want to have quotients. And then it's a pain for each definition to prove that it's coherent with a quotient. In some cases, we can just get rid of the quotient by finding another presentation with another eliminator, with an eliminator for the quotient.
Okay. Like a canonical representative for the equivalence class. And,
So how is it precisely related to classifying topos?
It is precisely, yes, of course, it is the same. Yes, because in the classifying topos, you have all the quotients. You see, which you don't have in the syntactic category. You see, when you, in fact, what happens is this, like this question really is excellent because it allows me to explain a very important point, which is how we get from the syntactic category to the classifying topos. In fact, so categorically speaking, this has the structure of a geometric category. So what does this mean? So it means that here we have finite limits, which essentially correspond to conjunctions. Then we have images of arrows. And these more or less correspond to existential quantifications. So these images are stable under pullback. And moreover, we have unions of subobjects. And this corresponds logically to disjunctions. And these also are stable under pullback. So this is the categorical structure we have here. As you can see, quotients are not in this list. But quotients appear when you go at the classifying topos level. So in fact, this is an extension of that. So this embeds, this is fully faithful. And in order to obtain this from that, essentially what you do is to first add all the coproducts. So it's like disjoint unions of formulas. And then you take all definable quotients of them. Definable means that the equivalence relation by which you quotient should be defined like syntactic by some formula. So you see, if you wanted to work with quotients that don't exist here, or more generally, don't exist in a site that you use to present the classifying topos, you should work at the topos level. Here the quotients exist, they are actual objects of the topos. And then of course you can move to another site where these quotients actually exist. So your technique is exactly, it fits perfectly into that. Because from what I understood, you see, you start from a category in which the quotients don't exist, and you replace it with, so you see, what we would do is, okay, this category, we go to the corresponding topos. Here we have the quotient, and then we find another site which presents the same topos, but which is richer than that, because it is obtained by adding the quotients. So this is a very natural thing to do. So you see, suppose that here, for instance, you have an object and some equivalence relation on this object. Suppose you are in a situation like this, and this object like doesn't exist here, but it exists there. You see, then what is natural to do is to define a C to be like the completion of C by the addition of those things, but like here, you see, because you know that these things exist, so you can enrich, you can take D to be the full subcategory of this topos on the objects of the form this. And if you induce the topology from the canonical topology of the topos, you will get a site which presents the same topos. So yes, your strategy, in fact, I'm pleased to hear that you have already been using this kind of techniques.
Well, for very specific examples.
Yeah, of course, but they fit really perfectly, into that. In fact, I have been considering in my work many completions of this kind. For instance, in connection with Galois theory. In fact, I told you in the course, you were not there in the last lecture, but you can look at the slides because this is a precise example of adding quotients. You see, there are examples of Galois theories in different areas of mathematics, like Galois theory for Boolean algebras or for graphs, for finite graphs, for finite groups. So you have a Galois theory for finite groups, but in fact, you see the category of finite groups and embeddings in fact, lacks certain quotients. And so you don't get a full Galois theory as for fields. For fields, you have all the structure, you see, and so you have a perfect theory. In the case of finite groups, you have something that embeds into a Galois theory. And if you want to get a full Galois theory, you have to close under quotients. So what do? You go to the topos, you know that the quotients exist there, and then you add those quotients. And so this led me to introduce imaginary finite groups. So it's an extension of the category of finite groups and embeddings with new objects so that the quotients exist. And in fact, these imaginary finite groups are really definable in terms of the existing ones. So the construction is completely explicit. So you might enjoy this paper. So it's called the topological Galois theory. And it describes the general setting for constructing Galois theories and what to do in case certain quotients don't exist. The topos theory tells you precisely what you have to do, because in a sense, you know that the topos is the space where the quotients really live. So you know that how they should behave. You have like the right environment for considering that. And then, of course, because the topos is too big, you try to restrict to some smaller site that still has enough of the structure you need. And so, yeah.
Speaking of Galois, are you aware of Kevin Kappelman's work on Galois connections, transporting formulas from certain contexts to other contexts? So, like this example of when we take a quotient and then we want to work somewhere else, but it's A because all of our formulas.
No, I would be interested
you can transport between these two things, given that you prove certain connections.
No, I'm not. Which kind of tools does he use?
This is in Isabel Hall.
Okay. So I will be interested to look.
We developed like a significant mathematical theory beforehand, but also actually has an implementation in Isabel Hall which implements this stuff. So
this looks very interesting. So it might be that there is, from what you say, but it doesn't talk about a topos theoretic underpinning of. Okay,
it's
but
much more like
okay.
Ground level. So I'd be interested to know if there is some connection.
This is a very, very nice point. So I will ask you the reference to check. Thank you.
A question. So if I think about Morita equivalences and weaker notion that was what by
interpretability. Yes. Well, it's stronger.
Yes.
Yeah.
More restricted.
Yeah, more restricted. Yeah.
Anyway, so is it true? I had the feeling that the by interpretability would be the same as Morita equivalences if you fix the category of the site.
Yes. Indeed, because in fact, you see, it is a fully correct intuition, because in fact, by interpretability requires the equivalence to descend at the site level and not just to exist at the topos level. Existing at the topos level is weaker than for the equivalence to restrict them at the site level. Because in fact, in general, you cannot recover a site from a topos by saying we take those objects that satisfy such and such. In general, it is not possible. Therefore, you can have equivalences that exist at the topos level without them to restrict. So in fact, you see, it's very nice to have this broader notion of a Morita equivalence, because first you work at the topos level, because you know that if there is a semantic equivalence, well, you should see it at the topos level. So you take that point of view and then you try to get more concrete. So once you have established your equivalence, for instance, in this form, you might wonder, does this come from an equivalence already at the level of sites or not? So in general, I can tell you by no means. But you can still modify the site. You see, you can take something richer, or in fact, in general, when you have a category and the corresponding topos, it's extremely flexible, because in a sense, this is kind of, this is the generators and this is the completion. Now, whatever thing that you have between that and that, for instance, if I decide to add whatever thing from C, the important thing is that I have at least C, okay? But suppose I take C plus other things. It's fine. It will give me another site of presentation for the same topos. I will just have to take the canonical topology here on the topos, which is given by the epimorphic families, and I restrict this topology to that, and it will give me another site that presents the same topos. So as you can see, you have a great flexibility. So you can go from this broader view of Morita equivalences to a more concrete view of dictionaries. But you see, the point is that if you don't think in terms of Morita equivalences, you might find yourself with a lot of holes that you don't know how to fill. So in some sense, you lack the global view. You don't know the orientation, where to go, what to do. So in fact, the toposes provide you a very good guidance on, you see, how you should define quotients, for instance, or other kind of operations. And then once you have understood how they work at the topos level, you can try to restrict. This is like the main methodology.
And if we think again about the question about quotients,
Yeah.
Going from bi-representability to the more general notion of Morita equivalences,
yeah.
is saying that now we allow for having a different representations of our objects via, for example, representatives of some quotients. And
absolutely, absolutely, yes. Yes, 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 indeed. So in fact, these techniques can be useful, for instance, for getting new presentations for structures presented by generators and relations, because you see, the notion of site is like a general notion of generators and relations. When you have a category, it's like the generators and the Grothendieck topology you can see as relation, you see. And so when you get to the topos of sheaves, it's like you structure, you build the universal structure presented by generators and relation. Of course, it's a big universe, so typically you don't want to work with the big topos. It's good, I mean, to have the big topos for calculations, because if you work in a setting which is very restrictive, calculations become, you get impaired, you see, very, very easily, because you get holes and you cannot like compute very effectively. So the usefulness of the topos context is that because it is complete, essentially everything exists. So you don't have holes, you don't have the problem of checking that your quotients or your constructions exist. They exist by definition because everything you can essentially think it exists. Then, of course, the point is, okay, but something could exist at this level without descending at a more concrete site level. Yes, of course. Typically, it is the case. You see, when in my paper on Galois theories, I can tell you the greatest majority of Galois theories are imaginary Galois theories, in the sense that part of the theory is concrete, but part is imaginary, and you have to add it in order to, so, but at least you know how to do it. You see, suppose you didn't have toposes. You wouldn't even know how to, because in general, there are different ways in which you can compute a quotient. You see, there is no, you have no guidance on how to define it. In fact, the topos theory, for instance, tells you that, you see, suppose you want to consider some quotient here. Of course, topos theory invites you to choose an appropriate topology, because, of course, the quotient that you will have in the topos will depend on the choice of the topology. So you will not have just one notion of quotient. You will have, in principle, several notions of quotients. Of course, some more canonical than others. If you don't know what to do, you can take the canonical topology on the category. This is a very natural choice to make. But nobody prevents you from making another choice, you see. So you can control your choices, you have a guidance. See, in fact, for me, topos theory is especially interesting as a meta-mathematical subject, because it is a subject that guides your mathematical exploration. You are never blind when you use these tools, because essentially the ontology that they embody is the largest possible one. You see, when you construct the classifying topos of a theory, you see, even if the theory is contradictory, it always exists. If the theory is contradictory, it means that the classifying topos is trivial. It means that it has just one object. So the terminal object is the same as the initial object, which means that the theory is contradictory. But you see, it still exists. It's not that, you see, if you think classically, like, for instance, in terms of classical semantics, you don't see anything. You see, you don't see the theory, but the theory still exists. Even if it is contradictory, it has a dignity, you see? And so it's because of the connection with logic that the ontology of topos theory is, in a sense, the maximal one. And this computationally is extremely important, because the greatest difficulties that mathematicians, or also I would say computer scientists, even if I am not, face is because you lack some structure. You don't know if the choices you make are the right ones, because you have, you see, sometimes you are led to make ad hoc choices. If you have this kind of guidance, you will never make ad hoc choices. You let the theory choose for you. of course, you have to like feed the theory. You need to acquire some familiarity, of course, to run the machine. It's not that, but provided that you acquire this familiarity, then you have a wonderful resource that can assist and guide you.
Thank you very much.
Yeah, it has been a pleasure.